is Chapter 10. We're going to cover the basics of capital budgeting. We're going to evaluate the cash flows. So we're going to use the information that we've garnered all semester to calculate things such as net present value. So we're going to discount cash flows, subtract costs, and determine whether or not projects are good or bad. So capital budgeting is the process of evaluating and selecting long-term investments. These investments must be consistent with the firm's goal of maximizing shareholder wealth. A capital expenditure is an outlay of funds that are expected to produce benefits for a period greater than 1 year. Fixed assets are considered capital expenditures. An operating expenditure is an outlay of funds by the firm that will result in benefits within 1 year. The capital budgeting process consists of 5 steps. First, a proposal must be generated. New investment projects must be proposed. Second, review and analysis. The merits of each investment must be analyzed. Third, decision making. Firms typically delegate capital expenditure decisions based on dollar limits. Fourth, implementation. Expenditures are made and projects are implemented. And fifth, follow-up. Results are monitored. Projects may be independent or mutually exclusive. If projects are independent, then that means that accepting one project does not eliminate the others from consideration. Mutually exclusive projects compete with one another. Accepting one eliminates others from consideration. So, examples of mutually exclusive projects. If a firm needs increased production capacity, they could have one of 3 options. They could expand their current plant, acquire another, or contract with another company. If they choose one of these 3 options, they automatically eliminate the others. Most firms operate under capital rationing. This is the financial situation where a firm only has a fixed number of dollars available for spending. Numerous projects are going to compete for these dollars. So they only choose projects that have the highest, most stable returns. Unlimited funding is the financial situation where a firm is able to accept all independent projects that provide an acceptable return. They have an unlimited amount of money. If a company has unlimited funding, they operate under an accept or reject approach. They evaluate capital expenditure proposals and determine whether or not they meet minimum acceptance criteria. If they meet the criteria, they accept. If they don't, they reject. Most companies use a ranking approach. This is where capital expenditures are ranked on the basis of some predetermined measure, such as rate of return. So they would rank projects based on their rate of return and only accept the highest. So we're going to look at some different capital budgeting techniques. First, we're going to look at how to analyze cash flows. So here, Bennett Company, they have 2 possible projects. First, project A costs $42,000 and returns $14,000 a year for 5 years. Project B costs $45,000, returns $28,000 in year 1 and $12,000 in years 2 through 5. So we can put these on a timeline, just as we've done every other problem in this text. So project A. At time period 0, project A costs $42,000. That's a negative $42,000 for the company. And in periods 1 through 5, it returns $14,000. Project B, at time period 0, costs $45,000. In year 1, it returns $28,000. And in years 2 through 5, in year 2 it returns $12,000, and in years 3 through 5 it returns $10,000 each year. So we've just created our timeline. We can use this to evaluate the project using several different techniques. The first that we're going to discuss is the most simple, and it's the payback period. The payback period is the amount of time required for a firm to recoup its initial investment. So the company will determine a maximum acceptable payback period. It's arbitrarily determined. There's no rules. And if the company is able to recoup its initial investment within that payback period, then they would accept. If they aren't able to recoup their initial investment within the maximum acceptable payback period, they would reject the project. So we can calculate the payback period for each of these projects. For project A, calculating the payback period is very simple. Payback period for project A is simply equal to the project's cost as an absolute value divided by the proceeds each year. We can calculate payback period in this manner because the cash flows received in each subsequent year are equal to one another. So $42,000 divided by $14,000 is 3 years. So it takes 3 years for the company to recoup its initial investment. Calculating the payback period for project B is a tad bit more complicated. So calculating the payback for project B, we start with the cost. Project B costs $45,000. We recoup $28,000 of this $45,000 in year 1. So we still have $17,000 left to recoup at the end of year 1. In year 2, we recoup $12,000 of our investment. So we still have $5,000 left. $5,000 is less than the $10,000 you receive in year 3, so you divide by the cash flows in year 3 to give you 0.5. So it takes 2.5 years to recoup your initial investment with project B. So the payback period is 2.5 years. So you can see the payback method is very simple. It's computationally simple and very intuitive. It's often used by large firms to evaluate small projects and by small firms to evaluate most projects. By measuring how quickly the firm recovers its initial investment, the payback period gives implicit consideration to the timing of cash flows. But the payback period is usually used as a supplement to other decision techniques. The main problem with the payback period is that the maximum payback period is subjectively determined. The payback method is not based on the discounted cash flows to determine whether or not they add to the firm's value. A second weakness is that this approach does not take into account the time value of money. A third weakness is that the payback period does not take into account any cash flows that you receive after the payback period. So there may be a huge financial windfall at the end of the project's life, but that's not going to be included when calculating the payback period. So it's very easy to compute and very easy to understand, but it does have drawbacks. The primary benefit of using the payback method is that it allows you to use this in conjunction with more sophisticated techniques. So here, let's look at a few examples of why the payback period is not the best approach. First, we have Project Gold and Project Silver. Project Gold and Silver both cost $50,000. With Project Gold, you receive $5,000 in years 1 and 2 and $40,000 in year 3. So you recoup your entire investment in 3 years. With Project Silver, you receive $40,000 in year 1, $2,000 in year 2, and $8,000 in year 3. So it too has a payback period of 3 years. So both of these projects, according to the payback period, are equal to one another. The problem is that it's not giving any consideration to the timing of these cash flows. With Project Gold, you have to wait until the 3rd year to receive the $40,000. With Project Silver, you receive $40,000 right out of the gate. So it may make more sense to choose Project Silver over Project Gold, despite the payback period saying that the two projects are equal. A second problem. Here we have two projects, Project X and Y. They both cost $10,000. Project X returns $5,000 in year 1 and 2. So the payback period for Project X is 2 years. 10,000 minus 5,000 minus 5,000. That's 2 years to recoup your initial investment. With Project Y, they receive $3,000 in year 1, $4,000 in year 2, and $3,000 in year 3. So $3,000 plus $4,000 plus $3,000 is $10,000. So it takes 3 years to recoup your initial investment with Project Y. So according to the payback period, Project X is better than Project Y. But when you look at this, Project X in years 4 and 5 is only returning $100, while Project Y is returning $4,000 and $3,000 respectively. So it's returning a significantly larger amount of money. And these overall magnitudes of cash flows are not considered. One remedy is to use the discounted payback period. Here we calculate the discounted cash flows and then do the payback period with these. So here we have a project. It costs $100, returns $10 in year 1, $60 in year 2, and $80 in year 3. We can calculate the present value of these cash flows and then use them in the payback period analysis. So the present value of $10 so $10 divided by 1.1 is 9.09. The present value of $60 is $49.59. So 60 divided by 1 plus 10% squared. $49.59. The present value of $80, 80 divided by 1 plus 10% cubed, is $60.11. So you can use the present value of these cash flows in your payback period analysis. So we start with our $100, the initial cost. We subtract off the present value of the proceeds from year one. So $9.09, year one. That leaves us with $90.91 left to recoup. So we subtract the value in year two, the present value of the $60, the $49.59. That means that we still needed to recoup $41.32. $41.32 is greater than $60.11, so we divide. And we get 0.7. So it takes 2.7 years to recoup our initial investment when we're looking at discounted cash flows. 2.7 years. So we recover our investment plus our capital costs in 2.7 years. A more sophisticated measure is net present value. Here you subtract a project's initial cost from the present value of its cash inflows. So the net present value is equal to the present value of cash inflows minus the initial cost. This method is used by most large companies. It does take into account the time value of money. And the decision criteria is that if the net present value is greater than 0, we accept the project. If it's less than 0, we reject. So what that means is that if the net present value is greater than 0, the firm will earn a return greater than its cost of capital. It will increase the market value of the firm and increase the wealth of its owners. So using the same example, the Bennett Company, we can calculate the net present value. You've already used the net present value function on your calculator. Now we're just going to be including a cost. So we can use the NPV function on our calculator. First, we need to input the cash flows. Cash flows. To enter in these cash flows, you need to enter them into your cash flow worksheet. So when you push the cash flow button located next to the second button, it comes up and it says CF0. Previously, we always entered a 0 in or skipped this function, but it's simply the cash flow at time period 0. Here, we do have a cash flow at time period 0, and remember this is a negative. So it's going to cost $42,000, so a negative $42,000. Push enter and the down arrow. Cash flow at time period 1 is $14,000, and here you can save yourself some effort by using the frequency button. The frequency of the first cash flow is 5. Alternatively, you could enter in $14,000 5 times. So you push the cash flow button. To clear out your cash flow worksheet, you push the cash flow button and then second and clear work. Cash flow at time period 0 is $42,000. Negative, enter. Down arrow. Cash flow at time period 1 is $14,000. Enter. Down arrow. The frequency of this cash flow is 5. Enter. Be sure and push enter after the last cash flow or it won't remember that you've entered it. Next, you push the NPV button and enter in a discount rate. Here we're assuming the discount rate is 10%. Enter. Down arrow. Compute. and you get $11,071. So this net present value is greater than 0. So if these projects are independent, project A would be accepted. Push the NPV button, enter in your discount rate of 10%, enter in the down arrow and compute, and we get NPV equal to $11,071.01. Remember the steps if you have a graphing calculator: NPV, the interest rate, comma, cash flow at time period 0, comma, cash flow at time period 1, cash flow at time period 1, 2, etc., separated by commas, close braces, comma, open braces, frequency of cash flow 1, frequency of cash flow 2, etc. So here it would be NPV, open parentheses 10, comma, negative 42,000, comma, open braces 14,000, close braces, comma, open braces 5, close braces, close parentheses. And you should get $11,071.01. We can do the same thing for project B. The cash flow at time period 0 here is a negative 45,000. Cash flow at time period 1 is 28,000. That has a frequency of 1, so you can skip the frequency button. Cash flow 2 is 12,000, frequency of 1. And cash flow 3 is 10,000 with a frequency of 3. So push your cash flow button, second and clear work. 45,000 negative is the cost. Enter and down. Cash flow at time period 1 is 28,000. Enter. Down arrow. Frequency is 1, so down arrow. Cash flow 2 is 12,000. Enter. Down arrow. The frequency is 1, so down arrow. Cash flow 3 is 10,000. Enter. Down arrow, and the frequency of this cash flow is 3. Enter. Push NPV, enter in your discount rates, enter, down, and compute. And you get $10,924.40. So if you have a graphing calculator for the second option, you do NPV 10, comma, negative 45,000, comma, braces 28,000, comma, 12,000, comma, 10,000, close braces, comma, open braces. The frequency of the first cash flow is 1, frequency of the second cash flow is 1, comma, and the frequency of the third cash flow is 3. Close braces, close parentheses. I get so many questions because people forget to put the commas in. You do have to put commas between every cash flow and between the brackets and the interest rate. Once you have these entered in correctly, you should get $10,924. If these projects are independent, then project B is acceptable because it has a net present value greater than 0. If these projects are not independent, meaning that they're mutually exclusive, by accepting one, you reject the other. Project A is better than project B because it has a higher net present value. $11,071 is greater than $10,924, so we would choose project A. So the rule is, is that if projects are independent, we accept projects if they have a net present value greater than 0. If they're mutually exclusive, we accept the project with the highest net present value. So the next method that we're going to use is the Profitability Index. The Profitability Index is equal to the present value of cash flows divided by the initial cost. The rule is that we accept projects that have a profitability index greater than 1. So the higher the profitability index, the higher the ranking. So there's one cheat way to calculate this. The profitability index, since you've already calculated net present value, is equal to net present value plus the absolute value of the project's cost divided by the project's cost. And again, here I like to put the cost in absolute values, because when we think about this in a timeline, we usually consider cash outflows to be negative. So here we have our project A and project B, the same ones that we've been using. Remember, project A, the net present value was $11,071, and project B, the net present value was $10,924. So the profitability index for project A is equal to the net present value. Profitability index is equal to net present value plus the absolute value of the cost divided by the absolute value of the cost. So for project A, the profitability index is 11,071 plus the absolute value of the cost, so 42,000, divided by 42,000. So that gives us 53,071 divided by 42,000 to give us 1.26. Profitability index of project B is the net present value, 10,924, plus the cost of 45,000 over the cost of 45,000 to give you a profitability index of 1.24. So again, the rule is, if these are independent, you accept projects with a profitability index greater than 1. You can also use the profitability index to rank projects. So we would accept a project with the highest profitability index if they were mutually exclusive. So if we could only pick one of the two, we would accept the project with the highest profitability index, which is project A. Again, this is the same conclusion we got with net present value. Economic value added is a close cousin of net present value. It starts the same way as net present value. We calculate cash flows, but we subtract from those cash flows a charge that the investors demand on the project. So economic value added calculates the pure economic profit, the profit above and beyond the normal competitive rate of return in a line of business. So here we can calculate economic value added. Suppose a project costs $1 million. After that, it will generate cash inflows forever, perpetuity, remember that means forever, of $120,000. The firm's cost of capital is 10%, so we can calculate the NPV and the economic value added. Remember, NPV is the present value of cash inflows minus the cost. The present value of a perpetuity is its cash flow divided by the discount rate. And from this, we subtract the $1 million. So that gives us $1.2 million minus $1 million, so $200,000. You would accept the project. Economic value added. We have $120,000 that we receive every year. From that, we need to subtract the rate of return investors demand from their $1 million investment. They demand 10% of $1 million, so $100,000. So $20,000. So there's going to be economic value added of $20,000 per year. So it's going to be per year forever, so we can calculate the present value of these cash flows. So the economic value added for the project's entire life would be $20,000 divided by the discount rate, because again, this is a perpetuity, and the present value of a perpetuity is equal to its cash flow divided by its interest rate. So $200,000. So you get the same answer either way. But the economic value added tells you that this project earns more than its cost of capital each year, so it's worthy of pursuing. Another resource that we have is the internal rate of return. This is also a sophisticated technique, and it's the discount rate that causes the net present value to equal 0. So it's the rate of return a firm will earn if it invests in the project and receives the given cash inflows. The discount rate that causes the net present value to equal 0. So we simply take the cash flows and discount them by the internal rate of return and set that equal to the cost. And that is our methodology for calculating internal rate of return. It's very simple to do on your calculator, but the decision criteria is that if the internal rate of return is greater than the cost of capital, we accept the project. If it's less than the cost of capital, we reject the project. This guarantees that the firm will earn at least its required return. If the internal rate of return is greater than the cost of capital, the market value of the firm will increase, and so will the wealth of its shareholders. So the rule here, if the projects are independent, you accept all projects where the internal rate of return is greater than the cost of capital. If it's mutually exclusive, you accept the project with the highest internal rate of return, given that the internal rate of return is greater than the weighted average cost of capital. So we can calculate internal rates of return for our same example, Project A and B for Bennett Company. To calculate internal rate of return on your calculator, you simply have to enter in the cash flows, just as we did previously. Cash flow at time period 0, a negative $42,000. Cash flow at time period 1 is $14,000 with a frequency of 5. Push the cash flow button. Clear your work. So 42,000 negative, enter in the down arrow. 14,000, enter, down arrow, frequency of 5, enter. Now you push the IRR button and compute. And you get 19.9%. Okay, so my PowerPoint stopped working. Give me just a moment. So the internal rate of return is 19.9%. We can do the same thing for our second project. The cash flow at time period 0 is a negative $45,000. Cash flow at time period 1 is $28,000. Cash flow at time period 2 is $12,000. Cash flow at time period 3 is $10,000 with a frequency of 3. So cash flow, clear your work. and you get 21.7%. So if you have a graphing calculator, you choose IRR, cash flow at time period 0, comma, braces, cash flow at time period 1, comma, cash flow at time period 2, comma, as many as there may be, close braces, comma, braces, frequency of the first cash flow, comma, frequency of the second, comma, etc., close braces, close parentheses. So for the second one, it would have been IRR, open parentheses, negative 45,000, comma, braces, 28,000, comma, 12,000, comma, 10,000, close braces, comma, open braces, 1, comma, 1, comma, 3, close braces, close parentheses. So remember the rule. If the internal rate of return is greater than the cost of capital, here our cost of capital has been 10%, then you accept the project. Both of these projects have internal rates of return greater than 10%, so if the projects are independent, you would accept both. If the projects are mutually exclusive, meaning you can only pick one of the two, then you would pick Project B over Project A because it has a higher internal rate of return. So one thing to note here is that using the internal rate of return methodology, you get a different result. Internal rate of return says that you should choose Project B. Net present value said choose Project A. So these conflicting rankings are not unusual. Oftentimes, the internal rate of return will rank projects differently than net present value. It will give the same accept or reject decision, but it may not rank projects in the same order. They do, however, reach the same conclusion about the acceptability or non-acceptability of projects. It's better to use net present value than internal rate of return. So here's an example to show you why. We have a 10% cost of capital. A large project costs $100,000 and returns $50,000 a year for 10 years. This large project has a positive net present value of $207,000. It has an internal rate of return of 49.1%, so it's acceptable. The small project, you invest $1 and earn 60 cents a year for 10 years. The small project has a very small net present value of $2.69, but the internal rate of return is 59.4%. So according to internal rate of return, you would accept the small project and forego the large. According to NPV, you would choose the large project and forego the small. Obviously, the large project would be superior to the small project. Here's an example. Tony is evaluating an investment opportunity. He feels this investment must earn 9%. The initial investment would be $7,500, and he would receive $500 a year for 4 years, $700 a year for the following 3. He plans to sell the investment at the end of year 8 and get $9,000. So we can determine whether or not this is acceptable. First, we need to put this into our cash flow worksheet. So at time period 0, Tony would spend $7,500. Time period 0, he's spending $7,500. He receives $500 a year for 4 years. For years 5 through 8, he's receiving $700. But in year 8, he's also going to sell the investment and receive $9,000. So if we were to put this in our cash flow worksheet, cash flow at time period 0 is a negative $7,500. Cash flow at time period 1 is $500 with a frequency of 4. Cash flow at time period 2 is $700 with a frequency of 3. And the cash flow at time period 3 would be $9,700. So if we use the IRR, push your cash flow, clear it out, 7,500 negative, enter down. Cash flow at time period 1 is 500 with a frequency of 4. Cash flow at time period 2 is 700 with a frequency of 3. And the third cash flow is 9,700. Enter. So push IRR and compute, and you get 9.54%. So because the 9.54%, the internal rate of return, is greater than the 9% he requires, you would accept the project. Greater than 9%, so you would accept. So if you had a graphing calculator, you would put this in as IRR, initial cost, negative 7,500, braces, 500, 700, 9,700, close braces, comma, open braces, frequency of 4, frequency of 3, frequency of 1, close braces, close parentheses. And you should get 9.54%. 9.54% is the interest rate that would cause the net present value to be equal to 0. Net present value profiles are graphs that depict the project's net present value for various discount rates. We can create these net present values for our chosen projects. So discount rates can be arbitrarily chosen. If you do them in Excel, you can start at 0% and work up by 0.5% all the way to 30%. It doesn't matter, just so long as you cover a wide range. Here we chose 19.9% and 21.7% because these were the internal rates of return for the projects. But again, if you were in Excel, it would not take any time at all to calculate the net present values for a wide range of discount rates simply by clicking and dragging. So here we can calculate net present values. All you have to do is enter in the cash flows into your cash flow worksheet, push NPV, enter in various discount rates, enter down and compute. So for example, for project A, you would enter in your cash flows. Cash flow at time period 0 is a negative $42,000. Cash flow at time period 1 is $14,000 with a frequency of 5. You push NPV, enter in a discount rate of 0, enter, down, and compute, and you'll get a net present value of $28,000. Now it's easiest to go through and calculate all of these at once for each project. So to calculate the net present value at 10% for project A, you simply push the net present value button, enter in 10, enter, down, and compute. And you'll get 11,071. At 19.9%, you get 0. That was the project's internal rate of return. Remember, the internal rate of return is the discount rate that causes the net present value to equal 0. And at 21.7%, you'll get a negative $1,650.46. So you can do the same thing for project B. You'll get 25,000, 10,924, 1,375, and 0. Then you graph these. Project A has a higher net present value if the cost of capital is less than the crossover rate. Project B has a higher net present value if the cost of capital is greater than the crossover rate. So we can determine this crossover rate. You simply find the cash flow differences between the projects, enter these differences into the cash flow register, and calculate the internal rate of return. You can subtract Project A's cash flows from Project B, or vice versa. It doesn't matter. You just have to be consistent. If profiles don't cross, then one project is always superior to another. So we can calculate the crossover rate. We simply take the difference in the cash flows in each period. So at time period 0, Project A returns $42,000 to negative $42,000, and we subtract from that Project B's cash flows of a negative $45,000. So negative 42 plus 45 is 3,000. Cash flow at time period 1, take the 14,000 and subtract the 28,000. You just have to be consistent. A from B or B from A, it doesn't matter. So negative 14,000. Cash flow at time period 2, it's going to be the 14 minus 12 to give you 2,000. Cash flow at time period 3 is 14 minus 10 to give you 4,000. Now these cash flows remain constant at this point, so we can just do a frequency of the third cash flow of 3. So clear your cash flow worksheet. 3,000, 14,000 negative, 2,000, and 4,000 3 times. Push IRR and compute, and you get 10.72%. So if you have a graphing calculator, you would have put IRR 3,000, comma, braces, negative 14,000, 2,000, and 4,000. Now if you didn't want to mess with frequencies, you could just write the 4,000 3 times. It doesn't matter. Or you could use the same way I showed you before. Close braces, close parentheses. And you should get 10.72%, which is where the lines cross one another. It's the crossover point. So what does this mean? It means that if the discount rate is less than 10.7%, you would choose Project A. If it's greater than 10.7%, you choose Project B. For normal independent projects, if the net present value says accept, then the internal rate of return is going to also say accept. So if the projects are independent, it doesn't matter which methodology you use. You're going to get the same accept or reject decision. If projects are mutually exclusive, then you use net present value, because net present value is going to rank the projects more accurately than internal rate of return. And I'm going to explain why now. So these rankings can conflict because of differences in the magnitude and timing of cash flows. The primary cause of these conflicting rankings is the assumption concerning the reinvestment of intermediate cash inflows. So the cash flows that you receive in the middle of the project, so after you've already accepted it and before the project's over, those intermediate cash flows, the treatment of those is what causes the conflicting rankings. Net present value assumes that these intermediate cash flows are reinvested at the cost of capital. The internal rate of return assumes that they're reinvested at the internal rate of return. So it's more appropriate to assume that these intermediate cash flows are being reinvested at the cost of capital. It's not good to assume that they're going to be invested at the internal rate of return, because this may be an extremely good project that may come about once every 20 years. So you may not have the ability to earn this great of a return later. So it's more appropriate to assume reinvestment at the cost of capital. So here's an example. We have a project that costs $170,000. It's going to return $52,000, $78,000, and $100,000. The net present value at 10% is $16,867, and the internal rate of return is 15%. So according to both NPV and IRR, this project is acceptable. So if we assume that these intermediate cash flows are going to be reinvested at the cost of capital, the future value of these cash flows would be $248,000. If they were reinvested at 15%, the internal rate of return, the future value would be $258,000. So you earn an extra $10,000 using the internal rate of return as the reinvestment rate, which may not be realistic. So we choose to use the net present value as our methodology of choice when the projects are mutually exclusive. If we looked at these as returns, we would see that choosing the reinvestment rate of 15% is going to give us a greater return than choosing the reinvestment rate of 10%. So another reason why internal rate of return and net present value may rank projects differently is because of the timing of these cash flows. When a large portion of the cash flows arrive early in a project's life, the NPV will not be particularly sensitive to the discount rate. The net present value of projects with cash flows that arrive later on in the project's life, however, will fluctuate more as the discount rate changes. The differences in the timing of cash flows between the two projects does not affect the ranking provided by the internal rate of return method. So here, if we're looking at the different projects again, according to internal rate of return, project B is always better than project A. If we use the net present value method, however, it says that project A is better when the discount rate is less than 10%. If the discount rate is greater than 10%, project B is better. So it's giving you a more accurate presentation of the data. So net present value profiles can cross because of size differences. Smaller projects free up funds at time period equals 0 for investment. The higher the opportunity cost, the more valuable these funds. So a high discount rate or a high cost of capital is going to favor small projects. A second reason is timing differences. Projects with faster payback periods provide more cash flow in early years for reinvestment. So if the cost of capital is high, these early cash flows are especially valuable. On a purely theoretical basis, the net present value is better because it measures how much wealth a project creates. And there are certain mathematical properties that may cause a project to have multiple internal rates of return. More than one internal rate of return from a capital budgeting project will result when the cash flows follow a non-conventional pattern. The maximum number of internal rate of returns for a project is equal to the number of sign changes in its cash flows. So having a cost, a negative cash flow, followed by a series of positive cash flows, followed by another cost and more cash inflows is going to cause a situation where multiple internal rates of return can exist. Financial managers often prefer the internal rate of return simply because they prefer to work with rates. Another benefit of internal rate of return is that it does not require you to estimate the cost of capital prior to calculation. You don't have to enter in any discount rates to start with. You can calculate the internal rate of return and then compare that with the numbers that you calculate later with cost of capital. A scale problem occurs when two projects are very different in terms of how much money is required to invest in the project. In these cases, internal rate of return and net present value are again going to rank projects differently. Internal rate of return will favor small projects, and net present value will prefer the investments that make the most money. So in a recent survey, CFOs were asked to determine which methodology they use. They could pick multiple choices. 76% preferred, or 76% use IRR and 75% use net present value. One approach that you can use to remedy the internal rate of return is the modified internal rate of return. Because the internal rate of return overstates the expected return for accepted projects, because it's assuming that the intermediate cash flows are being reinvested at the internal rate of return, we can use the modified internal rate of return. This is the discount rate that causes the present value of a project's terminal value to equal the present value of its cost. The modified internal rate of return assumes that cash flows are reinvested at the cost of capital, not at the internal rate of return. So modified internal rate of return correctly assumes reinvestment at the opportunity cost. And it also avoids the problem of multiple internal rates of return. So because managers like rate of return comparisons, the modified internal rate of return is better than the internal rate of return. Calculating modified internal rate of return, however, is not simple. There are multiple steps involved. First, you have to calculate the present value of all cash inflows. Then you use the present value to calculate the future value. The third step is enter in the cost of the project as the present value. And the future value is the value you calculated in step number 2, and you solve for the interest rate. So we can do this example. Same projects we've been looking at. So we have our cash flows. We'll look at project B first. I've already gotten the steps written down. So if you have a graphing calculator, we already know how to do the cash flow functions. We've already done it on our calculator. This methodology here that I have written down, this methodology shown here is only usable if you have the professional version of the BA2+. If you don't, then we have to follow the steps up here outlined. If you have a graphing calculator, you simply calculate the net present value of the cash inflows. So here's the discount rate. Cash flow at time period 0, you put in as a 0 because that's a cash outflow. Followed by the cash inflows, 28,000, 12,000, 10, 10, and 10. That gives you the present value of these cash flows to be $55,924. Now you calculate the future value of this. So you set the present value equal to $55,924. The interest rate is 10%, and it's 5 years, and get the future value of this $55,000. So now for your present value, you enter in the cost, the negative $45,000. The future value is this future value you calculated in step number 2, and it's equal to 5, and you calculate the interest rate and get 14.89%. So if you don't have the professional version of the calculator, you put in cash flow at time period 0 is 0. Cash flow at time period 1 is 28,000. Cash flow at time period 2 is 12. And cash flow at time period 3 is 10,000 with a frequency of 3. And solve for the present value. So our cash flows. First clear it. So 45,000 negative. 28,000 with a frequency of 1. 12,000. And 10,000 with a frequency of 3. Push the NPV, enter in your discount rate, down arrow, and compute. I'm sorry, I put in a cost and I wasn't supposed to. That's 0. NPV, compute, and you get $55,924.40. I'd written 0 as a cost, but I entered in a number. So you get $55,924.40. Now we need to follow these 2 steps right here. So our net present value, we've solved for that. You simply push the PV button now. Well, I thought that you had to push clear once and then the PV button. So we've set in our present value, same as our net present value. N is 5. The discount rate is 10. The payment is 0. And we compute the future value. Compute the future value. Let's see. And you get $90,066.81. So remember the way your calculator works. Either the present value or the future value has to be negative. So here, you push the clear button and you clear your time value of money. We enter in the cost as a negative present value of $45,000. That's the cost of this project. The future value is going to be the present value of all cash inflows, the $90,066.81 calculated in step 2. The payment is 0. The N is 5, and we need to compute the interest rate that makes this work, and that's 14.89%. So for project B, the modified internal rate of return is 14.89%. So for project A, the modified internal rate of return is going to be 15.27%. And I'll show you how to do that on the next slide. So we enter in our cash inflows. Cash flow at time period 0 would be 0. Cash flow at time period 1 is $14,000 with a frequency of 5. Push your NPV button. Enter in your discount rate. And you should get NPV equal to $53,071.01. So now that's step 1. Step 2, we set the present value equal to the $53,071.01. N is equal to 5. The interest rate is 10. Payment is 0. And we need to calculate the future value. And you should get $85,471.40. Here I get that as a negative in my calculator. That's fine. We just need to change it to a positive in step 3. Step 3. The present value is going to be equal to the cost, the negative $42,000. The future value is a positive $85,471.40. N is 5. The payment is 0. And we calculate the interest rate that makes this work. And you should get 15.27%. So according to the modified internal rate of return, project A is better than project B because it has a higher modified internal rate of return. So we discussed situations where internal rate of return may have more than one value. And those are for non-normal cash flow projects. So this is where there are multiple changes in signs. So usually there's a cost, some positive cash flows, and then another cost. Normal cash flows are a cost followed by a series of positive cash inflows. So there's only going to be one change in the sign. So here, the first line here, this is a normal cash flow pattern. There's a cost with a series of inflows. Non-normal, cost, inflows, cost. Another normal, a series of cost with a series of inflows. Or a series of inflows with a series of outflows. So here there's only one change. Non-normal, cost, inflow, cost, inflow, cost. So multiple changes. So here's an example. We have a project that costs $800,000, returns $5 million in year 1, and costs $5 million in year 2. You can calculate the net present value and you'll get a negative number. which makes sense. But if you enter this into your internal rate of return, you're going to get an error, and that's because these are non-normal cash flows. So at very low discount rates, the present value of cash flow 2 is large and negative, so the net present value is going to be 0. At very high discount rates, the net present value again is going to be 0. In between these two discount rates, the second cash flow is going to be hit harder than the first, so the net present value is going to be greater than 0. And so the result here is 2 internal rates of returns. When more than one solution exists, the calculator is going to display the solution closest to 0. If there is a situation where there will be multiple internal rates of return, so a non-normal cash flow pattern, you just use net present value. Another situation that can occur is unequal lifespans. So here we have mutually exclusive projects with unequal lives. The short project costs $100 and returns $60 in years 1 and 2. The long project costs $100 and returns $33.50 for 4 years. The cost of capital is 10%. So the net present value of the long is greater than the net present value of the short. But is the long truly better? To determine this, we need to use the equivalent annual annuity approach. So when you choose between projects, between mutually exclusive projects with different lifespans, you use the equivalent annual annuity approach. You convert the present value into a stream of annuity payments with the same present value. So for the short project, you would say n is equal to 2. The interest rate is 10. The present value is equal to the net present value. Here we'll put this in, and it doesn't matter if you choose positive or negative, you'll get the same, but 4.132. And the future value is 0. By putting the net present value in as a negative, it's going to cause you to have a positive payment, which may be more intuitive to understand. If you solve for payment, that is your equivalent annual annuity, and you get 2.38. We can do the same with the long. N is equal to 4. Again, the interest rate is 10. The present value here would be a negative 6.19. That's the net present value. Future value is 0. And we solve for payment, and we get 1.95. So the short project has a higher equivalent annual annuity, so it is a better project than the long. Another option is simply to repeat the short. So you could repeat the short after 2 years to generate additional profits. Equivalent annual annuity is one choice. This is the second choice. So here, we started the project, cost $100, returned $60 for 2 years, and at year 2 we started it again, so it cost $100 and returned $60 for 2 more years. Calculate the net present value of this stream of cash flows, and you get 7.55. When you compare this to the large net present value with 6.19, you see that the small is superior. This may not be completely accurate because the cost may rise. So here let's do the example again. But let's assume that the cost of the second time that you repeat the project is going to rise $5,000. So instead of costing $100,000, it's going to cost $105,000, but the returns are going to stay the same. That causes the net present value to drop to 3.415, which is now less than the long net present value of 6.19. So instead you would choose L now. If you didn't want to repeat the projects, equivalent annual annuity would be a better approach. Another methodology that we can use is economic life versus physical life. So let's consider a project with a 3-year life. If terminated prior to year 3, the machine will still have a positive salvage value. So this is asking whether or not you should always operate an asset for its full physical life. So at year 1, the project cost $5,000, but it's worth $5,000. At year 1, the project has returned $2,100, but still has a positive salvage value of $3,100. At year 3, you've spent $5,000, in year 1 you got $2,100, in year 2 you've gotten $2,000, but it's still worth $2,000. If you operate the machine for its full physical life of 3 years, you've generated these cash flows in column 1, and it's now worth nothing. So this is what the cash flows would look like. The project cost $5,000, returned $2,100 in year 1, $2,000 in year 2, and $1,750 in year 3. That would give us an NPV of a negative $123. If we terminated after 2 years, we've spent $5,000 on the project, gotten $2,100 in year 1, received $2,000 from operations in year 2, and salvaged the machine for $2,000 to give you $4,000. So that's $2,000 plus $2,000 there, which would give you a positive net present value of $215. If you terminate after 1 year, you've spent $5,000 on the asset, you've received $2,100 from operations, and you've received $3,100 in asset salvage value. That's $2,100 plus $3,100. And the net present value of that is a negative $123. So this project is only acceptable if it's operated for 2 years. A project's physical life is not always equal to its economic life. So finance theory says to always accept positive net present value projects. 2 problems can occur when there isn't enough internally generated cash to fund all positive net present value projects. We can have an increasing marginal cost of capital, or we can face capital rationing. So the marginal cost of capital may increase because we are having to raise these funds externally. These externally raised funds have large flotation costs, therefore increasing the cost of capital. Investors also perceive large capital budgets as risky, and this is again going to drive up the cost of capital. If external funds will be raised, then the net present value of all projects should be estimating using this higher marginal cost of capital. Capital rationing may exist because the company may not choose to accept all positive net present value projects. The company will set a limit on the total amount of capital expenditures that it can make, and so they will rank projects and choose the projects with the highest net present value. So companies may face capital rationing because they want to avoid the cost of issuing new capital. So the solution would be increase the cost of capital by enough to reflect all of these costs, and then accept only the projects that still have a positive net present value. Another problem is that companies don't have enough managerial, marketing, or engineering staff to implement all positive net present value projects. So here they would use programming to maximize net present value, subject to not exceeding the constraints on staffing. And finally, another problem is that companies may believe that the project's managers are forecasting unreasonably high cash flow estimates, so they will filter out the worst projects by limiting the total amount of projects that can be accepted. A solution for this is to implement a post-audit process and tie managers' compensation to the subsequent performance of the project.